Okay, 9.5. Here we are going to take something a little bit different from the last video of 9.4. Different in the fact that they're going to be independent samples. So now on there I see testing mu with little 1 and testing mu with little 2. That means the mean from one sample and the mean from a second sample. Okay, there's no relationship between the two samples, so that's how they are independent of each other. For example, here's my comparison of incomes of individuals in two groups. How you split them up is all totally up to you. Lecture class may be divided into two groups. Maybe in one class I give them a different midterm, test the difference between the two scores. Okay, so independent studies that I'm not doing a before and after now. I repeat, not doing before and after, so they're not dependent. I'm going with two separate sample spaces, so they are independent. Now, when I collect those sample sizes, I have to pick the same n from each group. Well, I take that back. No, I don't. Testing the difference between the two means. Back to theorem 9.2. I don't have to worry about the 9.2. Just know this, that if I've got two distributions, distribution 1, distribution 2, they either have to form or follow the normal curve, okay? And I need to know these two standard deviations. Okay, and I need to know that they are going to come from two independent samples of size n1 and n2. Basically, whenever you see these little ones, that means it comes from the first population, okay, or the first samples. This is from the second population. So you'll see a lot of those little 2's that go along with that. We can do this difference of two means if we already know that there is a normal distribution. And again, like we've said before, we've got the population standard deviations. We could also use this if n1 and n2 are also bigger than 30 or 30 or larger. So we can use that central limit theorem if we didn't know that the original distribution was the normal distribution. Okay, so here we go. When testing the difference of two means, the null hypothesis actually indicates that there is no difference between the two means. So we're going to start off with either saying that mu1 and mu2 are no difference, or you could say that mu1 is equal to mu2. And I like to stick with that concept. So the null hypothesis is that mu1 is equal to mu2. You can have a left tail saying that mu1 is lower than mu2. You could do right tail, which is mu1 is bigger than mu2. Or you could have a two tail where they're different from each other. Left tail, right tail just kind of lets me know which area underneath the normal curve I need to find. Same thing with two tail. Okay, so here we go. I've got a college professor who wishes to determine at a 5% level of significance if there's a difference between the final exam results of these two groups of students. One group takes calculus in a traditional classroom setting. The other is taught through distance learning. Okay, so the following data is going to happen from, as you can see here. So traditional was a sample mean of 88 that came from 31 people. The population mean, or standard deviation, 3.3. Out of 30 people, they got an 85% on the final exam with a standard deviation of 4.1. Okay. Our null hypothesis is that these two test scores should be the same. Our null hypothesis is basically, is there any difference? So mu1 is different from mu2. So that means it's going to be two tail. Okay, X bar, my average of the first one, 88 minus 85. Now these are equivalent, so that's basically going to turn to 0. That's kind of a similarity that this is going to have with the dependent one, that second part just basically goes away, it turns into 0. So you can just take 88 divided by 85 and get 3 on the numerator. On by denominator, make sure you take the 3.3 squared, then divided by 31. 4.1 squared, then divided by 30, and then add them together. So if I'm working this out in the calculator, I'm doing 3.3 squared divided by 31. I'm going to hit enter, get that decimal. I'll take 4.1 squared divided by 30, divide that out, get that decimal. I'm going to add those two decimals together. Again, as many decimals as you think. I would say like 5 would be good enough, and then take the square root of that answer when I'm all done. So that bottom part becomes 0.9547. So that's kind of how I work that out. And when I divide those out, I get about 3.14. Okay, so again, my null hypothesis of they're equal, I'm testing that they're not equal. The difference of the two would be 3. The standard deviation part worked out to be 0.97. Get that all figured out, and I get a z-score of 3.14. Now, again, the reason why it's a z-score is I'm dealing with the two population standard deviations. Same thing as it was earlier in the chapter, same thing it was before in the previous chapter. So to find that p-value of two-tailed, I'm going to look up that area underneath the curve for 3.14. Okay, it's actually going to be a little bit quicker if I look up negative 3.14, because that's going to give me this area of 0.008, which is the same area as this. I'm missing 0 because of symmetry. I'm going to double it and get a p-value of 0.0016. Now I'm testing this at 5%, so that easily is smaller, so I'm going to reject the null hypothesis. Remember, the smaller your p-value becomes, the more likely you are going to reject the null hypothesis. So reject the null hypothesis. The statement shows that there's no difference between the two groups. Okay, we can conclude that the exam results for the distance learning are significantly different from the traditional group of 5%. How different? Well, we're not testing whether it's greater scores or less scores. We're just testing the fact that they're different. That doesn't mean that the populations are necessarily truly that way. It just means that these scores from these particular students would show that. All right, so testing the means when your standard deviations are unknown. So basically, you know, S1 and S2. So now we're back to T. Okay, simple enough. That's how it was before. We'll have 2 degrees of freedom. Okay, but of these 2 degrees of freedom, use the smallest one. Okay. Your null hypothesis, alternative hypothesis are all going to be the same concept. You're just figuring out t-score. So now it says, suppose that you do an experiment, the time in minutes for a headache to enter the bloodstream. The sample information is below, brand A versus brand B. Test the fact that B is faster. So we're going to say that the null hypothesis would be that their speeds are the same. If kind of intuit backwards thinking, but if B is faster, that actually means that this speed is slower than that one. So we're going to do one tail. Again, doesn't matter if it's left tail or right tail, because with a t-score they're going to be the same. And you're going to figure out this t-score essentially the same way you did in the past. I think these got lost in translation, but those should be X bars. So 20.1 minus 11.2. Okay, that's going to be minus basically 0 because they're going to be the same. The square root of your standard deviations of 8.7 squared over 12 plus 7.5 squared over 8. Okay, so numerator 20.1 minus 11.2, so that's 8.9. Okay. And again, the new denominator, I'm going to take the fractions individually, get those 2 individual decimals. And once I have those 2 individual decimals, then I'm going to add those 2 together. Okay, take the square root of that number, and we've got 3.652. Divide that out, and I get a t-score of 2.43. So there's my test statistic. I guess rounding it up, 4.4. We have degrees of freedom of 12 minus 1, 11, or 8 minus 1, which is 7. So use the 7 as your degrees of freedom. Go with the smaller one. So we're going to go for the row of 7, and we're going to see where 2.44 fits. Okay, 2.44 is between 2.365 and 2.998. So work my way up to the one tail, and the p-value is going to be between 1% and 2.5%. Okay, we're testing it at what level? I guess they didn't say. Oh, there we go. Level of 0.01. Okay, so 2.5% is bigger than that, so we would fail to reject the null hypothesis that the aspirins, or the, I guess, so brand A and B are working just as fast. As each other. Okay. So there we go. That's hypothesis testing when you have your S's instead of sigmas. Okay. One more possible test, and you guys figure out the pattern. It goes from z-score to t-score back to probabilities. Okay, so we're back to probabilities, and we've got a z-score. What this is, it's a group is sending out, county clerk wishes to improve voter registration. One method is to send reminders in the mail to people who are eligible to vote. A random sample of 1,100 people, which is 500 from one group, 600 to the other. Add them up, and there's your 1,100. Was randomly divided. One group, potential voters, had no registration reminders, and they got there and registered at a rate of 248 of them. So let's go. P hat 1 is 248 over 500. Okay, you have your 600 voters that received a notice or a note, and they got 332 of them to register out of those 600. Okay, we'll turn those into decimals here in a little bit. We are going to report, well here, null hypothesis. If the means were equal, their probabilities are assumed to be equal. Your alternative hypothesis was the proportion of voters who registered greater in the group that received the reminder. So the group 1 is the one that received the reminder. So P1 is greater than P2. So that is going to be left-tailed. Okay. And if you see, I wrote this hat over above it, or bar. This is P bar. So P bar is actually an average of your successes, which would be 248. There's R. And your 332, there's R also, over the two ends combined. So in this case, 1,100. Okay, so I'm going to go through and just figure out some decimals here. So we'll go 248 divided by 500. Your p hat as a decimal is 0.496. Keep all those. Your p hat 2 is 332 divided by 600. That's going to give you 0.55 with a 3. My P bar is 248 plus 332. Divide that by 1,100, and that's going to be 0.527. Q bar is actually going to be 1 minus that, so 1 minus that number, 0.47, we'll go 3. So z-score, 0.486, there's our first p hat. Our second p hat, 0.553, divided by the square root of p bar, 0.527 times 0.473, all over the n that they came from. So the n was the first group, 500. Okay, I'm going to run out of room, so I'm just going to extend my fraction. It's going to be the same products up above, but now over the 600. Okay, and again, we're going to subtract the difference of the means, which is going to work out to be 0 in the anyway. So on the numerator, 0.486. Yeah, I got a negative 0.067. Again, I'm going to work one fraction at a time. I'd multiply first and then divide by 500. I got 4.9 e to the negative 4th, that's scientific notation. I'm going to leave in my calculator like that, or you could write it out, I guess. It's 0, 0, 0. I just moved the decimal to the left 4 spots. Okay, same thing here. I got scientific notation, but I moved the decimal over to the left 4 spots, and I got that. So I'm going to add those 2 decimals together. Then take the square root of that answer, and I get 0.03009, but that should be good enough. So negative 0.067 divided by 0.03. Okay, I get a negative 2.233. Remember, it's a z-score, so I'm going to look up negative 2.233, and I could just take that area right there. That's going to be my p-value. So negative 2.233 is 0.129. So is 0.0129 greater than our level of significance of 1%? It is, just barely. So we are going to fail to reject. And I'll let you elaborate on that a little bit more, but it's basically we're going to fail to reject that the reminder did anything to help voter registration, that people will register to vote regardless. Now, again, this is just one sample. If you do it again, you might get totally different results. Okay, here's your assignment, page 559. You got some odds in there, 1, 3, 11, and 19. You got some evens in there as well. I would strongly suggest working through a bunch of these and come to class with as many questions as you got.